Remember that we described the microscopic state of a system by giving the values of the list of quantum numbers that belong to that system, and the number of quantum numbers values we have to specify was the number of degrees of freedom. Now we are going to address the issue of how we can describe the microscopic state of a system in terms of classical mechanics. So this is the question we would like to answer. How does one specify the microscopic state of a system described in terms of classical mechanics? As opposed to quantum mechanics. So in order to demonstrate this, let's say that I have a single particle that is moving in one dimension. And this is a classical particle. I call Q the coordinate of the particle's position. So this can be x, for example. It can be x, y, or z, but it's one-dimensional motion. So it's either x or y or z. So it's the coordinate of the particle's position. And I call P the corresponding momentum. So I have two numbers. One, the component of the coordinate of the particle's position, and P the corresponding momentum. Now, if I specify for this particle the position as a function of time and corresponding momentum as a function of time, this is going to give me a complete classical description of this particle. So you can see that here I have the PQ phase space. So this is momentum. This is the coordinate of the position Q. And I divide this space into small areas, and I locate the position of my particle in this phase space if I specify the momentum and so if I specify the momentum of the particle and its corresponding position as well. So here is Q, here is just the reverse. This is Q, and this is the corresponding momentum P. So this is for one particle, so one particle system, particle 1 momentum and particle 1 position as a function of time. So the particle, as it moves in one-dimensional space, will be going in between different cells in this PQ phase space. So this is PQ phase space. It's a two-dimensional phase space where we have delta Q and delta P as our unit for the cells, and their product is H0. So I have subdivided this PQ phase space into small areas. So PQ phase space is basically divided into small areas, and the area is basically given by delta Q times delta P is equal to H0. So this is my area of one cell in this phase space. And notice that this is basically dimensionally, if you remember, angular momentum is R cross with mv. Dimension wise, the area H0, dimension of H0 is angular momentum. So it is kilogram meter square per second square. Meter square per second. So this would be kilogram meter square per second as the unit. Okay, so if I want to specify the state of the system, then I have to give this pair of numbers P and Q. Then for this one particle, if I give you these pairs Q and P, position momentum pairs, implying that Q is going to be in the range Q to Q plus delta Q, where delta Q is a small number, and P is going to be, momentum is going to be in the range P to P plus delta P. Then basically this is going to describe the microscopic state of the system at this time t. So at a certain time t, I can specify the microscopic state of the system by giving you a pair of numbers for position and momentum, such that the position is with uncertainty delta Q and momentum is with uncertainty delta P. Now, is there any restriction on how small h0 can be, or how precise I know the value of Q and P? The answer is no. So classically, I can have h0, the area of one cell, as small as possible. It can be infinitely small. Quantum mechanically, on the other hand, there is a restriction that's given by Heisenberg uncertainty. Quantum mechanically, the uncertainty in position times the uncertainty in momentum should be greater than h bar, which is a reduced Planck's constant. H bar is h divided by 2 pi. Now let's generalize this to more than 1 degree of one dimension motion. So let's talk about a generalization of this idea here. Now I have an arbitrarily complex system. The system consists of many particles with a set of coordinates, with a set of f coordinates, let's say q1, q2, qf. This could be f particles, and I have f corresponding momenta as well. So this is going to be P1, P2, all the way up to PF. So the total is 2F numbers, because I have F is number of degrees of freedom, and basically this is going to be giving me F pairs of values Q and P. Now for each coordinate and corresponding momentum, for each particle, ith particle position, ith particle momentum pair, let's say, I have delta Qi times delta Pi is equal to H0, a constant. So if I give you these values, Q1, Q2, QF, P1, P2, PF, this is going to specify the state of the system. Now notice that this Q1 could be X1, Q2 could be Y1, Q3 could be Z1. If we are in three-dimensional space, example, this is for the first particle. Second particle, I can have X2, Y2, Z2, etc. And then I would have PX1, PY1, PZ1, PX2, second particle Y, Z2, etc. So that eventually I would have how many values? So since I have F is the total number of pairs that I'm going to get here, for n particle system, you would have for each particle three pairs, x1 px1, y1 py1, z1 pz1. F would be equal to 3n, right? So let's keep that in mind as an example. All right, so this is going to be corresponding to points in space where I have F Q values and F corresponding momentum values. So I have a space of 2F dimensions. So for the first particle X and Px, I would get a two-dimensional phase space. And if I include Y and Py as well, it will be four-dimensional, because I have to specify four dimensions: X, Px, Y, Py, etc. So it will be a phase space of 2F dimensions. The phase space will be divided into cells. So the phase space is divided into delta Q1, delta Q2, delta QF, delta P1, delta P2, delta PF. That means H0 to the power F volume cells. So that's going to be the cell volume. All right, so this is going to be our generalization. So how do we specify the state of a system for this general case? Well, we can summarize as follows. The state of a system in classical mechanics can be described by specifying the particular rth cell of volume h0 to the power f such that delta qi delta pi is equal to h0 in phase space in which the coordinates and momenta of the system are found. So this basically gives us the classical description of the state of the system. So all we need to do is to tell you where, in which cell the system resides. So if I tell you all the values of Q1, Q2, QF, P1, P2 to PF, and then that basically corresponds to a particular cell in the 2F dimensional phase space, and that cell is basically giving me the state of the system. So in a sense, the classical description is similar to quantum description. So I can say that the classical description I find for the state of the system is similar to the quantum description, which is given by specifying the values of f quantum numbers however, we have one difference. In quantum mechanics, the quantum numbers are discrete. The quantum numbers are discrete, so they can take only integer values, and delta q times delta p is greater or equal to h bar. We have Heisenberg's uncertainty. In comparison, in classical mechanics, the pairs of values that we give, position, coordinate, and momentum, corresponding momentum, these are continuous variables. They are not discrete, and there is no limit on how small their uncertainties can be. So there is no limit on delta q and delta p. So that's the main difference. So let's summarize what we said. We're trying to describe the microscopic state of a system that can be basically discussed using classical mechanics, the laws of classical mechanics. The simplest possible system is a single particle, a single classical particle that's moving in one dimension. If you know its position and if you know its corresponding momentum, as a function of time, you have a complete classical description. So if you look at the state of the system in one particular time, t equals t0, q has a certain value, p has a certain value, and you plot p versus q in the pq phase space. This is one dimensional, so this is just basically in this example, q would be equal to x and p would be equal to px if it's moving on the x-axis. Then you have a particular value q1 and p1, and we see that if we divide this phase space into cells with area h0, which is equal to delta Q times delta P equal area cells. And if I tell you in which cell the particle resides, that means I'm telling you its position is in the range Q to Q plus delta Q, and corresponding momentum is in the range P to P plus delta P, which gives the microscopic state of the system. And notice that the area of one cell is the product of momentum with position that gives me dimension-wise angular momentum. And classically, this area can be as small as possible. Quantum mechanically, we have a limitation, Heisenberg's uncertainty. Delta Q times delta P should be greater than or equal to h bar. If I generalize this to an arbitrarily complex system with total f coordinates and total f corresponding momenta, so that means I have two f numbers, and f is the number of degrees of freedom. For example, q1 could be x1, q2 could be y1, q3 could be z1, x, y, z coordinates of the first particle. q4 could be x2, y2, z2, etc., and the corresponding momenta. So for an n particle system, I would have three pairs for each particle, x1, px1, y1, py1, z1, pz1. For capital N particles, I would have 3n pairs. So that would mean the number of degrees of freedom is 3n. And so that corresponds to 2f dimensional phase space. So if you have two numbers, x1 and px1 versus x1 in the phase space, that is two-dimensional. If you have y1 and py1 as well, then you have to specify four numbers, that becomes four-dimensional. So in f number of degrees of freedom, you have 2f dimensional phase space. And this phase space is subdivided into cells with volume h0 to the power f. So that means Q1 should be in the range Q1 to Q1 plus delta Q1, P1 to P1 in the range P1 to P1 plus delta P1, so on and so forth. So if I tell you in which cell the system resides, then basically I describe the microscopic state of the system. And this is very similar to quantum mechanics, where I have to specify the values of f quantum numbers. However, the difference is that these quantum numbers are discrete, and delta Q times delta P is greater or equal to h bar. I have Heisenberg's uncertainty principle. In classical mechanics, momentum and position are continuous variables, and there is no limit on how precise I can be in measuring the values of Q and